So, anyways, thanks everybody for coming today. Um, we're going to go ahead and get started. I'll keep an eye on the room in case people join a little late. But with that being said, I'd like to welcome John Wason here today from Wason Technologies. He's been a big time collaborator, both in our collaborations with Rensselaer Polytechnic University, or Institute, sorry, and obviously on just Tesseract in the open source space, leveraging his Robot Rocketeur set of tools, as well as doing a lot of really interesting work with Python bindings and an open source teach pendant and utilities to support that. So he's agreed to share some of that work today. So John, are you ready? You can start firing up the screen share. Thanks for
Yeah.
coming today.
Okay. I think that should be shared.
Yeah, it looks
Um,
good.
so today I'm going to talk about my contributions to Tesseract, primarily in Python, Robot and the open source teach pendant. I'll start by introducing my business to people who haven't worked with me before. Wason Technology is founded in August 2011. It's a unofficial spinoff from RPI. I founded it my last year of grad school, and I'm currently visiting research at RPI. And I work very closely with Rensselaer Polytechnic Institute, and we've done a lot of projects over the years together. My company mainly does engineering services and consulting, and I'm also developing some software products. Of course, I'm maintainer of Tesseract, and my contributions to Tesseract are mainly the Python wrappers, adding multi-platform support, and the RoboRaconteur server. I also developed RoboRaconteur, which I invented in 2010. Um, the Teach Bennett we talked about. And I'm also a contributor to ROS working groups. So, for instance, we had the hardware working group for a while that I was contributing to. So, about myself, I'm a robotics engineer. Uh, so, I specialize in kind of lower level and system level work. So, I do mechatronics, software engineering, dynamics control, embedded systems, and networking. I'm the owner of Wason Technology. As I said before, I'm founded in 2011. This is sole proprietorship. And I founded it to commercialize technologies I developed as a graduate student. And I previously worked for RPI as both a research engineer and a graduate assistant. I did interns at JPL, and I have a PhD in mechanical engineering from RPI. So why I'm interested in Tesseract. So I needed a planner for RoboRaconteur. So RoboRaconteur does a lot of work with multi-robot systems and industrial robotics, and those systems really do require some method to plan in environments containing obstacles. And RoboRaconteur does not include ROS-RMW or any of the ROS core libraries by default. So the standard MoveIt was really not going to be the solution for my needs. And students at RPI needed access to collision detection and path planning that can be used from Python. Because they in general, although it's improved in the last few years, but in general, the students do not have a really strong C++ or computer science background in the group I work with. So really something that's a simple Python library would be very useful for that group. And we use it quite a bit during our ARM projects in the past. And as I said, MoveIt doesn't really meet these requirements. So MoveIt's really deeply integrated into ROS. And I think they have Windows support now, but Windows support's been shaky in MoveIt over the years. So, having the portability and multi-platform support is very important for us. And so I provided development support for the Python bindings, Windows and Mac OS support, and the RoboRaconteur, as I said before. And that's really what I've been working on since we started working together. I think it was 2018 was our first project where we started using Tesseract. So we had a ARM project with RPI, GE, Swery, and myself, and a few other organizations. We did a wind blade assembly project, and you can find videos and details about that on YouTube and on the ARM website if you're interested. And Southwest Research has participated in a lot of projects with with the RPI and myself over the years, including that first project and also projects for the RoboRaconteur itself and the open source Teach Bennett. And Tesseract has received some support over the years from those projects. So the real result that's just available now is the Python library. And what's very cool about the Python library is that it's fully self-contained. So when you install it using Python pip, you don't need to have any other dependencies installed beyond just the Python runtime. All of the required dependencies are included in that package. And I think I'll talk about that a bit later, how that works. Yeah, okay. So the Tesseract underscore Python is the package that provides the bindings, and I use Swig to generate the wrappers and alternative PyBind. Uh, so there are some advantages and disadvantages to Swig. I mean, the main advantage is it automatically parses the header files to generate the bindings, so you don't have to do a lot of handwork to assemble the bindings. It also supports multiple languages, programming languages, so you could use like C# and Java fairly easily from the same bindings. So I use Swig and Tor to implement some of the wrappers for like Python and C# support. The disadvantages is that it has a very high learning curve for the special markup language, and you have to do a lot of work with low-level type maps. And I think PyBind has some improvements on this, but there are some trade-offs in terms of what functionality you get with each tool. Now, the wrap Python bindings are essentially C++ and Python. It's a very low-level binding, and this can cause seg faults if you're not careful, because the life cycle of the objects is actually C++, not Python. So I think there is a need to develop a higher level interface which wraps these lower level Python classes to provide a more consistent experience. But that's a pretty tall order to do that. So we have done some work with that for the General Robotics Toolbox or RPI. There is a Tesseract module now, which will provide some collision checking and planning using the types from that class or from that package. There's a Tesseract VR Python package. It provides a very simple standalone 3D viewer. It does support VR, and I'll show a demo of that in a few slides. It's very cool to walk around the robot in VR, and it was actually very simple to implement. The Python package is available for Windows, Linux, and Mac OS, both on the Intel and the new Mac Silicon chips. It's available on pypy.org. You can just pip install it's actually called Tesseract Robotics package, but you can install it in a few seconds to have the full planning environment available. So the self-contained packages are made using tools called Audit Wheel on Linux, Delve Wheel on Windows, and Delocate on Mac OS. And what those tools do is they search the dependencies of the native libraries, and then they pull in the dependencies, and they do something called name bangling, where they add some extra random letters to the name of the libraries, and then they update the references, and that avoids collisions with the system libraries, but still allows you to contain all of the dependencies. So we did some fiddling with the plugin loading to statically link in those libraries so that they would be pulled in by these tools. But again, this allows you to have the full planning environment installed anywhere in a few seconds compared to the painful installation process for moving it and getting it up and running. And basically the entire API is exposed. So that includes environment management for the scene and the geometry, collision checking, kinematics, and planning. So this is an example I'm going to show of the Python script. And the steps in the Python script are install the required packages. Import the required packages, initialize the resource locator and the files for the environment, which includes the geometry, initialize manipulator info, initialize the viewer, build the planner request waypoints, load the plugins for the task planner, and initialize the pipeline, execute the request, retrieve the results, and display in the viewer. So unfortunately, I wasn't able to really include these in a clean way. So I'm going to just show the GitHub code. Can you guys see this okay?
Yes, it looks good.
Okay.
I mean, it's size font, maybe 8, but I can see it.
Oh, yeah, let me make it a little bigger for you guys. Okay, so unfortunately, it's pretty verbose. It's not super complicated. It's just there's a lot going on. So let me just sort of talk through the various steps of how this works. The top here is just importing all the various functions and packages you need to interact with the planner. And then there's a lot of comments in these examples to explain what's going on. Next, we load in the environment here. So we're loading in URDF, SRDF, and then the resource locator uses environment variable to specify where the like mesh files are. And we're doing some improvements to allow API modification. I think that got merged. So you can add the paths you want to search for resources here, and then you init the environment. Then you build up the information about the manipulator you want to work with. So the SRDF group, the name of the tool frame, and then the base link of your world. And then we initialize a simple viewer that I mentioned earlier. Initialize a robot starting point. And then we build up the waypoints. So I think this has actually been simplified because I think that Levi modified the way that the waypoints are polymorphic, so you don't have so many helper functions. But essentially, you're building out the waypoints you're interested in, and then the planning instructions, and you build up your program here. So this is kind of the meat of the process here, where you build up your request, and then you build up the plugin factory to load the planner. In this case, free space pipeline, which uses OMPL and TriJob to do the planning. And then you do some initialization stuff, and this is just some basic building up the request structure of what you actually want to do the planning. And then you build the executor and run the plan. And then you check to make sure you're successful at the end. And then you can retrieve the results and plot the motion in the viewer. Now, this is the raw low-level interface to Tesseract. And as I said, I think there's a need for kind of a user-friendly interface that hides a lot of this detail and provides a more Pythonic way. Because if you mess up the life cycle of these objects, it will segfault, because a lot of these are returning references from C++, which has no life cycle knowledge at all. So if you utilize an object after it's deleted, it will crash. So as I said, this is very much C++ in Python in the way that the life cycles operate, and also the way the API operates. Okay, so this is the viewer, which is a simple 3JS web viewer. And the way it works is it actually generates a GLTF file, which is a portable mesh format, and then transmits the GLTF into the browser. And then 3JS can very easily load in a GLTF file to display the scene. And I add some custom metadata so that the viewer knows where the joints are and where the links are to display and to animate. And then there's a WebSocket that allows you to add frames and motions to the viewer. Now, there's currently no user interface like in RViz. I think that's something I definitely want to work on. Now, the big advantages of a web-based viewer like this is that well, there are a few of them. One is it's really simple compared to native 3D programming. It's all JavaScript. 3JS is very high level. It's quite easy to uh, add features and display different objects in 3JS. The others is very portable. You don't have to fight the various APIs on different platforms. This will work on basically any platform that supports the standard 3D WebGL and Web GPU technology that's available in most browsers now. And the other reason is a lot of systems are headless these days, or you're in a Docker where you don't really have great access to um, the window system. So, for instance, in the Teachpreneur project, there is no monitor on the actual uh, runtime computer. You're just using a remote interface. And the other thing is there's no licensing issues like you have the Qt. This is all either built into the browser or it's just available on GitHub as open source. And as I said, there is a VR capability. I'm also demonstrating the orbit in 3JS, moving the scene around. And there's an enter VR button on the when there's a VR headset available. So this is my Quest 1. I'm demonstrating using the VR. So you can actually walk around the robot, and this is about 5-6 feet tall, the robot. So it's around the size of a person. And the new feature I've added recently is locomotion. So you can move yourself around in the scene using the right controller. So at first I was showing using the joystick to move forward, backward, left, and turn left and right. So that's a more standard interface. What I'm showing now is that you can actually drag the scene. So this is a control scheme which is inspired by something called Gadgeteer, which is a game in VR. So you hold down the B button, the scene will move as you move your hand around. So you can move, left, right, up, and down. And I found that to be a very effective scheme for trying to get some detailed, very, very small motions rather than large scale motions you would get with other control schemes. And 3GS does not have a great option available for that, so I came up with the scheme based on the Gadgeteer. So I think that's it for the Python. Are there any questions so far on the Python interface? Okay, so let's move on to Rope Contour. So, why is Rope Contour a useful technology? There's something called what I call an augmented object-oriented remote procedure call framework. And what this means is that you have objects on one of the nodes you want to access from other devices. And what RPC does is it tries to hide that layer between the communication layer. So it creates what they call a proxy or a reference on the client side, which exposes the same functionality as the object itself. And then the system automatically implements the communication layer. And this is a version of RPC which has been designed for robotics automation. And specifically, it adds support for streaming real-time data and also support for the types of data types you tend to transmit using for robotics rather than business applications. So, a lot of focus on numeric types and some of the geometry. It's a very small stand. Well, it's not it's very small. It's a small standalone libraries with very few dependencies. It's designed to be highly portable and embeddable. So it's widely available on the standard package managers. So it's in the Python package manager, the Microsoft VC package manager, the Conda Forge environment. It's available in the MATLAB third-party catalog, and it's in the .NET NuGet catalog. So you don't have to worry about lots of kind of exotic dependencies. It just sits as a normal library in your project. One of the real killer features is plug and play ability. So if you connect to a service using Python, MATLAB, or LabVIEW, the client interface are automatically populated. So you don't have to have any prior knowledge of the service types and the like. There's no message service files you have to have. It will automatically populate. And there's also standardized types for plug and play interoperability. So if you have a deployed device like a robot, there's a standard interface so you can have interoperability between different vendors. We found it significantly easier to use than ROS and ROS2 with a learning curve that students have usually picked up in a few days. And for simple client use, you can usually get going within a few minutes after installing the package. We've also found it's actually complementary with ROS and ROS2. So ROS and ROS2 work pretty well if you have like a closed system, like a single device. But for some of the large systems, we found that RoboRack is a lot better. So you can add or remove devices very easily, and it doesn't have some of the scaling issues you have with ROS. There's very wide platform support. So the three main desktop, or actually four main desktop operating systems, so Linux, Windows, Mac, and FreeBSD. It works on the mobile platforms for Android and iOS. And because it's object-oriented, when you connect to a device, you don't have to worry about trying to figure out topics or services. Essentially, the client and the service have a very strong demarcation. So you just connect as a client, and you can have pretty good granularity over, what clients have access to what features, and there's a permission system for, for authenticating clients. It works on embedded, so there's something like a RopeRack Controller Lite, which is a pure C implementation I'm working on, and that's now working on like the Raspberry Pico, and I'm working on the Zinc 7000 FPGAs, and also on an ST Ethernet embedded device using FreeRTOS and Light something other for the TCP stack. LWIP, that's what it is. Now, also, RopeRack Controller is interoperable with web, so you can connect using WebSockets from a browser, or you can connect to a web server, and these are all first class supported by all the nodes. So I have some longer presentations talking about these features, which you can see on YouTube. And there's a homepage you can take a look at, and a directory. So this slide is a much more detailed list of features. You guys can take a look at this if you want to, because it's kind of a long slide to go over. We've done a lot of ARM projects using RopeRack Controller. So this is a list of the various projects where Southwest has worked on quite a few of them with us. And I was going to say inclusion in the list does not necessarily imply endorsement. This is just a public record of who was involved in various projects. So for RopeRack Controller, I've been developing a Tesseract server, and this is still work in progress. It's not feature complete yet. Now, the server itself is developed in C++, but it can be accessed for any supported client language. So the current list is C++, Python, MATLAB, C#, Java, LabVIEW, and JavaScript, which is a bit of an asterisk in JavaScript. So it's not important now, but there's a bit of a weird way that's implemented. So one of the interesting features is that the client language does not need a library. So you don't have to use the Tesseract library on the client side. All the types are RopeRack Controller. And for Python, MATLAB, and LabVIEW, these are all automatically generated on the client side. And all of the nodes natively support being called from the web browser. So when we create web interface, you don't have to do any special work to have that capability. You can just connect to the to the service of the web browser and be able to interact with it. So that's how the open source teach vendor works. I'll talk about that in a few slides. Now, what's interesting is that RopeRack Controller allows you to closely follow the API of Tesseract. So the interface is a lot more similar to the C++ and Python interfaces as compared to the ROS interface. There are examples and the Docker runtime available in the repository, so you can just install the Docker and run the examples if you want to take a look. But currently, there's no viewer available, and future work is to adapt the the viewer from Python to work with Tesseract, and also to create a viewer for the general rubric contour use. So let's take a look at some of the code files, and we'll take a look at the service definition, which is how you define the interface to uh, Tesseract, and also the Python client example. Let's take a look at the service definitions. So the service definitions are the interface definition language for rubric contour, and this is specify what you want to expose. Let's take a look at the environment. Well, actually, let's take a look at the base class first. So this is the base interface you connect to when you connect to Tesseract, the Tesseract service. And essentially you have, this is used to give metadata for all devices rubric contour, which support the more sophisticated interface. And then you have some metadata about what's available on the server. And then objref allows you to access other objects within the service. So you have the environments and the executors here. Give you guys a few seconds to digest that. So if you go to the environment, this is what the functions available in the environment look like. So essentially, it allows you to get the current state, get the join link info in the environment, and also apply commands to modify the environment. These are not actually printed yet; they're just entered into the IDL. Now, this is still somewhat limited. I think we're going to be expanding the functions available in the environment, but this is very close to the architecture of Tesseract itself internally. So here's what the environment commands look like. So essentially you have the mirror of the various environment commands that are available in the C++ API. Now, rubric contour supports variant types. So as you can see, all of these are var value types, and that means you can have any valid data type to transmit. So rubric contour only sends by value types and by objects that are passed by reference to the client. And then you have the command language. And these are the waypoints and the instructions, which are defined in Tesseract. And then for the composite structure, you have the list of instructions which you would want to send for a planning operation here, and also how you receive the results out of the planner. And then finally, you have the executor, which is how you actually execute a plan operation. So you have the executor input, and you fill in the various data, and then you execute using this function to actually run the operation. And then you have the result. Now, I think that the Tesseract API is changing this. This will have to be updated to better match the Tesseract API. So anyway, as you can see, the interface is very close to what the internal C++ API looks like. And here is the Python client example. And there is also C++ client example in this directory. And you can also, as I said, do C# and LabVIEW pretty easily using the interface, although it is a bit verbose. So here's how you would actually interact with the service. So you connect here using a URL. You can also discover using some of the connectionless options. And then these are some helper classes just to make it easier to work with standard types. And this is how you retrieve the proxy types from the service when you are using plug and play. So um, because you don't have any information before, you have to pull dynamically out the types here, and then you build up you request the task pipelines. So you find the output key. You load one of the environments, and then there's a helper function here to build a move instruction. So you're just building up a structure. They're using a var value here. Now, Python does not carry enough information for robot controller to know what type you're using. So you have to use this container to specify what you want to interpret this value as, because the Python is kind of ambiguous. You build your instructions, you build your manipulator info, and then you build up your composite instruction with the instructions for the move. And then you build a planning problem with the composite instruction as the input and the environment name and the manipulator info. And then you pull out the object reference for the default executor, and then you execute. Or sorry, you build up the last input, then you execute it. Now, robot controller supports something called generators, and generators are a special function where it returns an object you can call run or next on multiple times. And the next function can take a parameter and or return a parameter. And this is modeled after the Python generator and coroutines. And this allows you to have long-running operations where you return status, or if you want to return a lot of data which is too big to transmit in one chunk. And this is kind of like an action, but has a different design structure. And then you pull out the results from the final return value from the generator. And as I said, unfortunately, there's no viewer available for this yet. That's kind of a work in progress. And the links are here. The PDF of the slides is in the chat if you want to pull down the slides and take a look at the links. And you can try Robot Contour using the training simulator, and the example is designed to work against the scene. So it'll move one of these robots. Okay. Are there any questions on Robot Contour before we move on?
I think that's a pretty good overview.
Okay, so I'll move on to the teach pennant, and this is the last piece we want to talk about today. And the teach pennant is built on Robot Contour, and it's kind of the high-level user interface. And the thing about Tesseract or Pyre is that everything is an API Robot Contour objects. You can actually get to all the functionality that you're commanding from the program environment using the Robot Contour client. So this is also a higher level interface to the motion capabilities of Robot Contour, rather than the lower level interfaces available from the robot classes. So I don't want to spend too much time on this because there are dedicated presentations, and this is still kind of under development. I'm hoping to work on this more over the summer to really get everything cleaned up and ready for general widespread use. But the basic architecture is you have a runtime computer, which has a lot of different Robot Contour nodes running to manage the system and all the features. And there's a sandbox, which actually runs the code. And the code is based on a restricted dialect of Python, so it strips out a lot of the features that you would trip up in a less experienced user and make it difficult to verify. So it's just like a very minimal scripting language. And this is the interface for programming using the Python dialect. And there are lots of soft keys to make it easier to use it with a tablet rather than with a keyboard and mouse. And there's also the Blockly interface, which basically is the same as a Python but in block form. So this actually compiles down to the same Python code uh, in the um, in that environment. So actually, Brock, who is on the call, did a lot of work on this with me a couple of years ago. So
So John,
the
is this, I mean, I can wait till the end, or can I ask a couple of follow-on questions based on this? You touched on it, right? So, or would you rather I wait?
no, go ahead.
Okay, so like obviously I've been excited, or I like the Blockly piece. Is it entirely is it entirely tied to the open source teach pendant, or can we like say create a way to leverage the Blockly interface, like say on like a standard UI on like say an operational cell?
Um, okay, so there are a couple. Blockly itself is just a standalone library available from Google. So we did not invent Blockly. We just
Correct.
leverage it.
Right.
And Blockly Blockly can generate out various languages, so it can generate JavaScript or Python or some other various backends. So we have a pretty sophisticated structure for doing plugins for Blockly, where we can easily add blocks to the environment and it'll have the correct backend to call into the Python. So essentially, there are two layers to our system where you have the what we call sandbox functions, which are functions you can add into the Python environment. And then Blockly can be configured to call those sandbox functions. So uh, if you want to use this code, you have to have the backend runtime operating for us to be able to ingest those blocks and execute them. Now, whether that's useful for your environment, I don't know. I mean, Qt does have a web browser uh, um, widget, so you can run the Blockly in there if you want to, but it just depends how much of this you want to suck into your system to leverage what we've done. Unfortunately, there isn't really we don't have an isolated C++ backend you can use for that functionality.
Okay, that makes sense. I was just curious, right? Because we run into a lot of entities that are trying to not rip the whole band-aid off at once. And I remember when this was coming together, it seemed like if I have an educational program that's already exposing folks to kind of like things that start looking like, code logic, but they still have come up through like say ladder logics or traditional teach pendant scripting. Blockly seems like a good stepping stone into more setting up advanced systems, right? But I wasn't sure like how explicitly tied it was to this project. But it sounds like there is some flexibility if other like say educational institutions wanted to like go like this sort of route. It could be an interesting pathway, right, to start like getting a little bit more into developing or interacting with advanced systems.
I mean, Blockly is all over the place. It's used in there's something called Scratch, which is the MIT
Yeah.
early programming that uses Blockly now.
Oh,
They
no
actually
kidding.
invented one of the earlier versions of this type of language, and then Google created Blockly, and they kind of backported that into their work because it's a lot more sophisticated what MIT had. And it's used in Minecraft, I think,
Yeah.
and I think it's used in a couple other. I think it's used in Roblox, maybe. It's something very similar is used in Lego now. So, one of the design ideas behind the Teach Pen, which never really fully explored, was almost everybody my age and younger, or a little older than me and younger, can operate like a very complicated video game. And the question is, what skills are they using to be able to operate that video game? And can we try to leverage those skills in the Teach Pendant? So we did as much as we could in in that sense, but I think that's an interesting way to look at it is, what pre-existing computer skills do kids have from playing games their entire childhood? And can
Yes.
we leverage that? Because it does develop a lot of spatial reasoning, to be honest. How can you take advantage of that in this environment? So
Right.
Blockly is more and more used for these more sophisticated games, and that's why we try to embed it in this.
Well, in the end, setting up robotic systems is just a different kind of game. No, thanks, John.
Yeah, much higher stakes though if you make a mistake. Okay, so just a quick overview of the Teach Bennett. So we did do some partial integration of Tesseract, but we never really fully completed that part of the project. Again, hopefully this year I'll be able to finish that out. And Sweary was part of that team, so Levi did a lot of work on Tesseract as part of this project. And this was during the pandemic, which is kind of a nightmare to be honest. Uh, so the implementation is it's a web-based user interface with a Python backend, and the reason for that is, as I mentioned before, a lot of devices are actually headless that we're working with, and or you want to operate in Docker, so it's much easier to have a web interface as compared to a more traditional Qt interface. So the browser actually runs something called Pyodide, which is a Python implementation compiled using WebAssembly and Emscripten. So this runs it allows us to run the same code on the browser and on the runtime. So it's significant amount of code sharing. Now, unfortunately, this has some implications for performance and memory usage, but for a single window on modern systems is such a big deal. And Robot Controller is in the Pyodide distribution by default, so you don't have to worry about compiling it. And we use Vue.js for the visual component system. And Vue is one of the major front-end design systems available, including React and Angular are the two other ones. And Vue is also out there, and Vue is a lot more modular than the other two options. You can just sort of sprinkle it in as you need it compared to React and Angular, which are really, full page frameworks. And Vue is actually used a lot by the Chinese companies, like I think it's Alibaba and what's the other one? Sorry, I'm blanking the other major Chinese company, but they use Vue a lot in those systems. So we use the robot controller standard types to add or remove devices, so you can add or remove devices at will. And this is a significant advantage over ROS, where robot controller doesn't try to subvert the same namespace. It's a very clear organization of what is a specific device and how you talk to it. And it also makes it much easier for doing discovery because you're only looking for that one object rather than trying to find every single function and topic available. And there's also a much easier deal with like firewalls because you're not trying to do forward and reverse connections. Everything is very strictly client service. Although there is some connectionless capability that's beyond the scope of what we're talking about today. The Pyre system can be extended using plugins and extensions for new features, and this is all in Python and is designed to not require expert level programming skills to operate the device or extend it. And as I said before, the web interface improves the headless and cross-platform capability of the system. This is a screenshot of the viewer running in Pyre, and this is actually an older version of the viewer. This is using Babylon instead of Tesseract for the 3D viewer, but we do have some blocks, but it was quite limited at that point. So, as I said, my hope is that this year we'll really dig into fully integrating the Tesseract into the Teach Bennett and try to really take advantage of those capabilities. And I'm hoping there could be some code sharing between the core Tesseract project and this application, so we're not wasting time, duplicating effort. Okay, so current and future work. I'm working on improving the drivers and components of robot controller ecosystem, so various robot support and various features. I want to complete the Tesseract robot controller service, including the viewer. And I also want to implement sort of a general alternative to RViz for my project. Unfortunately, RViz is not really portable for my needs either. It's too integrated to the ROS ecosystem. Continue developing the open source teach minute. And one problem I've run into, which I'm not sure if there's any ideas from the people on the call, is how to parameterize the posture or slash configuration for Cartesian waypoints. And that's kind of a nightmare in basically every robot I've worked on is how you define which of the alternative solutions you want to use. So I know Descartes is trying to solve that problem to a certain extent, but for a system where you have portability between different vendors, there's no good way available to really specify a desired configuration. Of course, if you change the robot, you're changing the kinematics and often the structure of the robot too. So, um, is any advice on that or previous work? I don't want to really dig into this. I'm sure there isn't an off-the-shelf solution available. And this is one of the reasons there isn't really a lot of Cartesian support in the teach pendant is I don't have a good way to represent the posture yet. I want to potentially add scene editing and waypoint selection or so definition to the viewer. So some of the features that like Robot Studio has where you can build up your scene and click on points to add frames would be good. Improve the scene and robot geometry file format. The URDF is not portable for my needs, so I may want to have the robot serve up a geometry file so that the viewer can add it in. And current URDF and SRDF is not capable of doing that. So I'm trying to figure out a better way to handle that and also be able to have enough geometry information to do stuff like, selecting waypoints because the current mesh files do not have information available. They're tend to be very tessellated and not have the detail we need. For Robot Couture, I'm working on the low-level real-time embedded and critical system support, and that's using the ANSI library that I'm currently developing. Training dissemination is a big one. I've not had a lot of users picked up in the last year or two, which just kind of surprised me given the capabilities of these systems. So I need to start doing a better job of advertising and helping with training. There is a new getting started document on the Robot Couture webpage, which has a lot of really good, starting information. I also want to create some YouTube training videos. Rust and Go support, language support is on my list. So I know Rust is getting a lot of pickup now, which is good because C++ is not particularly safe for the memory issues we're seeing these days. And Go is also increasingly getting support, although I'm not such a big fan of Go. I don't think it has any niche that really other products couldn't support. And I'm also trying to work on some products to sell to support the development of the technology. So Robot Couture for LabVIEW is now available for licensing on the website, and hopefully soon it'll be available from LabVIEW itself. So that's it for me today. And are there any questions?
Thanks, John. We can open the floor up to questions or any other discussion. So feel free.
Hey, John, thank you for the great presentation. I got a question regarding the delay of these developments regarding the Tesseract Python side and as well as the Tesseract Robot Contour integration. Since the Tesseract development is frequently changing and it includes API changes as well. So do you have a strategy to at least provide like rough delay time, or are you planning on developing some automating things to automatically deploy with the new API changes on the Tesseract maybe? I wonder your opinions on that.
Yes, that's probably a Levi question rather than from me, because I'm just sort of following what they're doing on the C++ side.
Yeah, so we're working to a 1.0 release. Probably, I imagine we're probably 6 months out on that. The goal is, and then that will be where the API will be more stable from that perspective. So we have a lot of things. There's an issue, I think, on Tesseract repo that's tracking the things that we want to get in, things that need to be changed or at least revisited to make sure that they are the structure we want moving forward. We've made good progress, but I imagine we're probably 6 months out to that 1.0 release for that. But once that gets in place, the ABI will be much more stable. We're also going to set up CI pipelines to check and verify that to make sure something doesn't get missed. So we're getting close, but probably about 6 months out.
Thank you.
Any other questions for John? Great. Well, either way, we'll have we'll post the recording up on the Ross Industrial YouTube channel. And John, as you get into the point where I know you have your flyers, for instance, obviously any other sort of like other brief write-ups or updates, keep us posted. We're happy to kind of like help drive awareness where we can. Like I said, via our Ross Industrial forums or any other tools. So yeah, keep us posted on your progress, and similarly, right, we'll continue to march along with obviously the Tesseract 1.0 release as well. If there should be some tighter syncing up there as well, just keep us posted, right? That's why we're getting together once a month, right, to make sure folks collaborating are making sure like we're kind of moving together. For those who didn't see it, I'm recopying the slide link. Oh, John already did. Thanks, John. So, right, there's nothing else. Yeah, we can adjourn. Levi, do you want to add a few like just kind of high level updates relative to Tesseract real quick?
Yeah, I can give an update. I guess, John, I do want to talk further on the UI aspect. I know we've had several discussions internally on what we do there from the web-based interface. So I think it would be good to maybe talk on your thoughts on it. I know we've talked internally. I think it's more around just what platform do we want to settle on? Do we want to go with something like I know Facebook's got one. There's several other like higher level tools, platforms that you can build this stuff off of, or I think there are some lower level ones that are more for research, but may not have all the nice bells and whistles. So I know we'd be interested to talk on that to kind of pick a direction forward on the web-based stuff. Related to Tesseract, so just so everybody's aware, we recently found a bug that most people may not been experiencing on how Trajopt and the profiles were being used. I think we've got everything merged in through planning. I'm working on getting all the ROS repos updated. There was quite a bit of changes that had to be made, but the main thing to kind of at the high level, if you were modifying like collision margin data through the environment, and then in your profile for Trajopt, modifying like pair collision margins, or I think it's more around the pair. If you were doing any type of like pair-to-pair special collision margins, if you were modifying those at the environment level, those were not getting used in Trajopt for planning. In all the planners, the way the collision configs were integrated was not done correctly. So So it was only using the collision margin pair data from the profiles, which did not capture anything that was in the environment. You can go and take a look at the most recent PRs on Tesseract and Tesseract planning if you're interested in that. But I don't know how many people were using special collision margin pairs. I do know several like companies that were, but most of them were doing it through the profile, not modifying the environment. So it's potential that some people may not be experiencing this bug, but it is possible. But I think that's the main update that we've been working on is getting all that fixed and updated.
What's the latest on any IFOP optimization, or are you kind of that's paused for right now, or?
Yeah, so I think we have a PR out there that's initiated the initial like low level stuff. It's now the main piece is to update all the costs and constraints to use the full data set to get us there. But the nice thing is now we've also made some changes as part of this. Is we've updated the profiles between the legacy TrajOpt and the TrajOpt IFOP. Those profiles are very similar. They're almost identical, I think. So one, this helps us for as we're making these changes to IFOP, we have a good way of comparing the two to make sure things line up between the two on that. And I do know we're planning to port the collision weighted sum work that we did in IFOP that was done correctly there to possibly to legacy TrajOpt, just to have a good one, like apples to apples comparison between the two, because we're trying to do a good job to make sure that things are one-to-one between the two versions as we're porting to IFOP. But I think the main thing for probably sunsetting the legacy is to get things updated, all the cost and constraints to use this new, they call them a variable set. So we need to update to the new variable set that manages things better, that should get us better performance in the legacy.
Perfect. Just so you know, we do have some funded work that may seek to leverage, well, it does leverage IFOP.
Okay.
David Mers is not here today, right? But if there's anything, perhaps like you guys should just chat as he gets spun up and ready to run some more tests. So for those who aren't aware, we've been doing some work with infrastructure-free mobile robot coordinated motion, where we leverage Tesseract and IFOP to basically enable treating a mobile base as a gantry. And so using it as like, if you think about like how we're doing motion planning in gantry-based systems, right? And we just treat the mobile base as a 3DOF gantry. And so we use IFOP for when like if the let's just say the mobile base is not exactly where we expect, we can basically use IFOP to like basically keep the toolpath following via trajectory mod of the manipulator, and then like start correcting and injecting corrections to the mobile base to keep things all running smoothly. And it's our demo platform. It worked really well. We're trying to migrate that. So we have like a small effort to port over to a diff drive platform, because before we did Omni, because we have a target use case we're looking to actually like get up to speed on and potentially like out sometime in the future. So the nice thing is like we might get to test this new IFOP implementation. There's a chance to make some commits along the way, right? So Levi, you can just kind of keep in the loop with David as he gets spun up.
Okay, yeah, that would be good. I mean, I think the infrastructure is in place now, and there's unit tests for the new variable set. I think it's just now we got to go and update the costs and constraints to use that. So yeah, that'd be awesome if we had an effort to go and do that.
No, perfect. And that's obviously whenever we can, like be it like robotic blending FTP or here on the COMOP program, we obviously want to walk the talk, right? So make commits back to the core repos as we leverage them. And so for those of you who haven't leveraged the IFOP, it's a really powerful tool set. This is just an example of a use case, like enabling coordinated motion. But there's a number of cases where we did some work as well, leveraging iFopt, where we could have our cobot application, say, with the proper data feed, actually plan around things in the environment. We were showing it, we're planning around a person, but it could be any other sort of like object that sort of, so to speak, shows up in your scene. So it's a really nifty tool set and has a lot of like interesting use cases. So yeah, we're pretty excited to get a chance to like test out this latest implementation.
Yeah, and the nice thing is there's an open PR that for the IFOP that's adding the Hessian support to it, which will further improve things for users. That'll be nice. A lot of the low level solvers support it. It just never was exposed in IFOP. So hopefully that'll be soon.
Great. Any other questions from the audience? All right. With that, we are over time, so I appreciate some of y'all hanging out. A little bit extra time. And again, I'll get the video cleaned up and I'll send a blast over our comms channels when it's published. And then John, I'll send you the link directly, of course, before we go live to make sure everything's cool. And then, and you may have, so for those who haven't seen it in the chat, John was kind enough to already share the slides. So I'll make sure I maintain this link as well in the YouTube comments for the video as well. So thanks everybody for coming out today. Thanks Levi for the update. John, thanks for putting together the materials. So look forward to seeing everyone next month.
See y'all. Thank you.
I had a quick question about the mobile manipulation you're talking about. Is there?
Sure, we can hang out. What's your question?
I think I'm working on a similar use case around mobile manipulation and exploring full body planning with the similar idea of like using the gantry like system. Even like we had a training with Michael when he visited here last year.
Yeah.
During ROS-Con. Like he also came to our offices here at TU Delft, and
right.
Yeah, we started working on it, but we haven't had a chance to catch up on it yet. But yeah, I think like, but we have finally found some time and budget to like work on mobile manipulation with full body planning. So just curious on like what you have and like see how we can, how we can contribute on that.
Okay, is that relative to, so obviously our work has been focusing largely on, hence the iFOP piece is involved because we're trying to do coordinated motion, right? So I guess like what is the scope of your mobile manipulation? Is it similar where you want to be like kind of in conjunction tying manipulator and mobile-based trajectories, i.e. leveraging, basically treating it as a gantry system? I think Michael's probably, it sounds like he spoke to you about that concept.
Yeah.
Okay.
Yeah, I think that's kind of the idea. But more of in a context of like a local planner, like from Nav2, like let's say I still want Nav2 to control the base when it's going everywhere else, but like once it's in a particular area, it should switch to this mode, and we want to use the full body capabilities without specifying like a more portion for a base and like a post for the and some trajectories for the arm. It'll be nicer to do this for ideally a non-contact process, but hopefully also contact processes in the future.
No, absolutely. And then Levi, we have a couple gantry examples in the Tesseract training docs. Is that correct? Does that sound about right? And that can be a good starting point to kind of see how you've set up Tesseract leveraging a gantry.
Yeah, so we do have, like in Tesseract examples, there's a low level, like leveraging iFOP. I think it's called the online planning example.
Yeah.
Is the one, and I believe that's the one probably Michael did with y'all. Is that correct?
I think we kind of provided our UIDF, like the robot I had, like the custom mobile manipulator we have with UR10. And like he kind of started making changes and like figuring out the Tesseract configurations needed for that particular setup. We didn't use the online planning example.
Okay. Yeah, so there is that example if you want to poke around with it, that's using the it's a 2-axis gantry system with, I think, an ABB robot on there, and
Yeah.
it uses like a cylinder as the collision object, and it's continuously planning a trajectory, and you can move it. The visualization is not as nice as it used to be. That's probably something we need to update on the GUI side, so you can actively see the updates. But I think that's the only piece that's not as nice as it used to be in the videos we showed.
Yeah.
It will post new trajectories to the trajectory widget, but then you have to go and look at those and play those. We've been talking about publishing just a marker that is multiple collision, like a trajectory marker. That way it would update dynamically for these type of cases where you want to visually see every update of the trajectory. That's probably a feature we need to add so to better demonstrate that example again.
Yeah, thank you. I think it'd be good to brush that up, and maybe I'll let you know where I am in the next meetup.
Yeah, if you're able to, I would start with the example and try to get it running. And then when it makes sense, we could talk about like how we kind of extended that or dropped in, so to speak, a base, like a mobile base instead of a gantry.
Yeah.
That's probably a reasonable progression. So get comfortable with like how it works, like in a traditional gantry setup. And then, we talk about like, oh, well, I have to like insert now like this mobile base and then do the associations between, how it was represented as a gantry to now like a mobile base. And so it's relatively simple and intuitive, but like it helps to kind of get understanding the traditional gantry problem first.
Yeah. Yeah, no, I appreciate it. Thanks.
Awesome. All right, everybody, thanks. And Nitish, if you have any questions, don't hesitate to reach out. It sounds like you already got Michael's contact information, but my contact information is all over the ROS-I website. So just reach out if you run any bumps in the road.
Yeah, of course. Thank you.
All right, nice meeting you, and good luck. We look forward to hearing more. John, thanks again. Brock, hey, long time no talk to. Good to see you again. Matthew, thanks for joining. And Levi, as always, thanks for sharing everything that's going on. All right, everybody, we'll be in touch. See everyone in about a month. Thanks.
Bye.